The International Space Station is one of the most complex objects ever created. A machine the size of a football field, built piece by piece in one of the harshest environments imaginable. And we have animated every step. Over 2 decades, using some of the most powerful rockets ever created, we launched hundreds of tons of equipment into orbit. Each truss, module, and power system maneuvered into place by robotic arms, often guided by astronauts' hands suspended in the void while hurtling around Earth at 8 kilometers per second. A one-of-a-kind construction problem. With the inherent vulnerability of life in orbit ever present, simple malfunctions become life-threatening problems. Minor damage caused by space debris can turn into a high-voltage repair mission, where one spark can turn an astronaut's oxygen-rich sanctuary into a nightmarish inferno.
And of course, my spacesuit has a Kevlar outer, but there are metal wrist disconnects and other metal parts of my spacesuit that could allow for electricity to conduct into the 100% oxygen environment of my spacesuit, which would be very flammable. That'd be a very bad day for me.
That's Dr. Scott Parazynski, a retired NASA astronaut who is the only person ever to both go to space and summit Mount Everest, flying on 5 space shuttle missions, and has visited the ISS twice. And I spoke to him to get some first-hand stories of what it's like to be strapped to the end of a robotic arm in space, trying to repair a damaged solar panel with spare parts. But the ISS is more than just a satellite. It's a home, it's a workplace, it's one of humanity's greatest achievements. The ISS has hosted life, science, and stories. But after decades of unprecedented international cooperation, its time is coming to an end. Soon, this orbital giant will meet its fate in the upper atmosphere, tearing itself apart in a fiery re-entry, destroying all that hard work in a matter of minutes. Before that final blaze, let's rewind time and dive into the monumental engineering challenge of building this machine. This is the incredible story of the ISS. In late 1998, a Proton rocket cracked the sky over Russia, carrying a strange new object to orbit. It was called Zarya, meaning sunrise. Zarya was no mere satellite. It was a powered spacecraft, a control module, equipped with attitude controls, batteries, fuel, solar panels, and propulsion. A starter engine for a space station not yet born. Just 2 weeks later, the space shuttle Endeavour launched from Florida, its gigantic cargo hold carrying the next module of the ISS, Unity. With the historic moment of the 2 internationally owned spacecraft coming together caught on film. Unity is a short, stubby, 5.4 meter long cylinder without much space for living or experimenting. Instead, Unity acts as a connecting hub. Along its walls, you'll see 4 docking ports, plus 2 more on its ends that in the future will all be used to build up the space station. Here it is in its current configuration on the ISS. But these docking ports could not be directly docked to the orbiting Zarya. Docking 2 spacecraft in orbit has never been simple. Long before the ISS, different systems were tried, each with their own limitations. The early Apollo and Soyuz craft used a probe and drogue, essentially a stick and cone that worked for small capsules but offered only a narrow passageway between vehicles. While fine for crew transfer or modest resupply, it wasn't designed to support the scale and complexity of a permanently crewed station. Later, during the Shuttle Mir program, American and Russian engineers developed the Androgynous Peripheral Attach System. The androgynous name comes from the fact that both the target and the receiving end look identical, with no male or female parts, with the goal of this being a universal docking system, allowing any 2 spacecraft to dock together, as Goddard intended. Each side had a ring with 3 petals equally distributed. One side extended its mating ring with a soft capture, where the 3 petals of each side come together and connect with these latches. At this point, the soft capture ring is retracted and 12 latches engage to form an airtight connection between the 2 spacecraft. The Mir station served as a testing ground for the ISS, and while the ISS was still in its planning stages, a Progress cargo ship slammed into Mir during a manual docking attempt, tearing into one of the station's modules. a stark reminder of how risky orbital dockings could be. Dr. Scott Parazynski was aboard the first mission back to Mir after this collision.
We didn't have the warmest physical welcome to the Mir space station when we arrived during STS-86. There had been this collision to the outside of the Spectre module, so you could actually see, even from quite a ways away, the solar panels on the outside of the space station had these through holes in them, and they were mangled. You could see sort of a divot in one of the radiator panels. This was a pretty beat up space station that we were approaching. On top of that, the orientation of the space station really was ajar. And as our commander, Jim Weatherby, was approaching, and I was supporting him using the camera systems and our computer systems to help make angular corrections to prepare us for docking. It was 6.5 degrees off axis. It was substantially off, really askew. And we weren't sure if there was a problem with our navigation system, with our sensors, or maybe the fact that the space station had been clobbered a few weeks earlier, that there was some other problem going on with the guidance, navigation, and control system of the Mir space station. Ultimately, we found out that the crew aboard the space station Mir had done a star alignment procedure. That's how you kind of coordinate or calibrate your systems. They had essentially chosen the wrong star.
Aboard the shuttle, the crew had to fly in their spacecraft by hand. The androgynous docking system depended entirely on both vehicles being perfectly aligned and flown together with precision. Using laser rangefinders and an onboard calculator, the delicate course corrections began to be made.
The final approach that we had to the Mir space station was very dynamic. Once you're on your approach, you're moving relatively slowly, but in relative space, but you're traveling at 17,500 miles around the planet, and you've got two enormous spacecraft with jet thrusters that you don't want to inadvertently fire and potentially damage a solar panel on the outside of their space station. You don't want to contaminate other parts of the space shuttle. And so there was a lot of hand-wringing, but we followed our training and our procedures. We were able to identify the misalignment between the two spacecraft. And Mike Bloomfield, the pilot on board, input the offsets that I was able to calculate using some grids on our camera systems, and we aligned the two docking systems exactly as they needed to be, and we came in for a successful docking. But it was certainly something that we had never experienced before in the Shuttle Mir program, and we were our hearts were racing. Let me just put it that way.
In the background, while these events are playing out, NASA had already started their own design of an American-only station called Freedom. NASA had already chosen a different mechanism to physically connect modules in orbit. They called it the Common Berthing Mechanism. This isn't a docking system, it's a berthing system. That means modules aren't flying in and bumping into the station under their own power. Instead, they're carefully grabbed and maneuvered into place. And it was a big improvement over Mir's old system.
But when you got into the kind of the core of the base block of the Mir space station, they had examples of probe and drogue docking systems, which actually required this large probe to be rotated inside the volume of the space station. It took a lot of space. It actually required some kind of interesting gymnastics and fancy flight to get around these probes to get where you wanted to go. So as this International Space Station was being engineered and built around the world, it was decided that it would be really important to be able to transfer very large installations, lab racks included, through hatches. And so we developed the Common Berthing Mechanism, which had a much larger cross-sectional area. It allowed us to essentially transfer things the size of, say, a telephone booth almost, full racks of equipment that would be kind of the cornerstone of the science and the operations of the International Space Station.
Later, in the International Space Station's construction, the Italian-built Leonardo, Raffaello, and Donatello modules used this larger berthing system to deliver tons of cargo to the space station. But the berthing mechanism doesn't come without drawbacks. The electric and fluid connections and bolting sequence take time to perform, so berthing is less ideal for emergency situations or rapid vehicle departure. Crewed missions still rely on the androgynous docking system. This is why Unity went up with 2 dongles attached to its ends. These are the first 2 pressure mating adapters that are still docked to the ISS. This side is attached to the androgynous system and the other side to the American berthing mechanism. Their small size and flexibility meant that over the construction of the ISS, they would be moved between nodes and attachment points to open up the possibilities for the space shuttle to dock anywhere. 2 modules were now pressurized, but before these modules were launched, one crucial decision had to be made. Where in the sky would the station fly? This decision began with NASA's Space Station Freedom. It was meant to fly solo in a 28-degree orbit, good for launching from Florida, but unreachable from Soviet launch sites in Kazakhstan. After the Cold War, plans shifted. The orbit changed to 51.6 degrees to bring in Russia. That number might seem arbitrary, but it was calculated down to the 10th of a degree. With this large inclination, the station passes more populated areas. The specific 10th of a degree comes because launching from Baikonur at exactly 51.6 degrees, the rocket would barely scratch the border of China. This ensured that no spent booster stages from Russian rockets would ever fall on Chinese soil. The 51.6 degree inclination affects how the station is oriented with comparison to the Sun and Earth, and that would bring some problems when the giant solar panels of the ISS were put in place, but more on that later. In the early 2000s, the International Space Station was still just a shell, 2 modules, quietly orbiting Earth, empty and incomplete. By the end of the year, it will become a home. Exhibition 1 was on the way, and that was about to add a lot more complexity to this operation. How do you turn an empty satellite into a place where people can live and work every day? To keep humans alive in space, the station needed power, control, air, cooling, and livable space, and all of that had to be up and running in less than 12 months. It started with Zvezda, launched in July 2000 atop a Russian Proton rocket, with the Pizza Hut logo plastered on its side to help offset the launch costs. Zvezda automatically docked here behind Zarya. It had an electrolysis system to split water into oxygen and hydrogen. It had carbon dioxide scrubbers, filters to manage humidity, and fans to circulate air that in 0G would not convect heat. It also carried part of the thermal control system, a liquid polymethyl siloxane loop that helped keep cabin temperatures safe and stable. With the station getting larger, it's nice to have a sense of direction. Like any other vessel, the ISS can be divided into port and starboard, and forward and aft, but in free-flying space, without a horizon as reference, 2 extra directions matter: zenith, pointing away from Earth, and nadir, pointing down toward it. Once the station had a habitable module, the next station was to add systems for control and expanded communications. During STS-92, the shuttle Discovery docked to the forward port of Unity. Using the Canadarm, astronauts removed a non-pressurized truss segment from the payload bay and mounted it on the Unity's zenith port. Because of its position, it became known as the Z1 truss. Since the truss did not fill the entire shuttle bay, the crew also brought up and installed a 3rd pressurized mating adapter on the opposite port, adding another docking point for future assembly missions. The Z1 truss carried the station's first control moment gyroscopes, designed to keep the station stable without burning propellant. But early on, there wasn't enough computing power to rely on them, so controls still came from the Russian section. Zvezda came with 2 main engines, each producing 2,300 kilos of thrust, and for precise orientation, the module uses 32 multi-directional attitude-controlled engines, each generating 13.3 kilograms. But every time the thrusters fired, they burned precious fuel that had to be replaced by resupply missions, not a long-term solution. The Z1 truss also carried the first communication systems. The S-band antenna handled voice and telemetry, linking to Earth through NASA's tracking and data relay satellite system. The Ku-band antenna allowed for video and science data to be sent down. The Z1 truss also served as a temporary structure rising above Unity to hold early solar panels and supply power until the main truss system was ready. Exhibition 1 arrived at the ISS aboard Soyuz in late 2000, but the station could only handle basic life support at this point. Its small solar panels couldn't power Unity, so the crew lived mainly in Zvezda and Zarya, relying on Russian systems. A month later, Space Shuttle Endeavour was going to dock to the ISS, bringing supplies and the first of the US-made solar panels. But before the shuttle could dock, one more obstacle had to be cleared. The Progress resupply ship, docked at one of the few available ports, was in the way. There weren't many places where the bulky space shuttle could safely attach to in the still small ISS, so Progress had to undock and drift in a temporary orbit, waiting for its turn to return. The first set of large solar panels arrived, rolled up in an unpressurized structural segment called P6. It was installed in a temporary position here atop the ISS. The name itself gives away its final location, P for portside and 6 for its future spot at the very end of the station's sprawling port truss structure. But back then, that part of the structure didn't exist yet, so P6 had to wait, sitting here powering the young station until the rest of its backbone was assembled. Eventually, the relocation of these panels would cause massive problems. To store the power these panels generated, the station used nickel-hydrogen batteries, each holding about 81 amp-hour, to keep everything running during orbital night. But more power also meant more heat. In space, heat doesn't just drift away, it has to be radiated. So, the truss also carried one loop of liquid ammonia to absorb and expel heat, radiating it out into the cold vacuum. In February 2001, during STS-98, the space shuttle docked in this port below Unity. In its payload bay, it carried Destiny, the next US module and the future hub of American science in orbit. Using the shuttle's Canadarm, astronauts rotated the module and attached it here onto Unity's forward port. The pressurized mating adapter, which had been temporarily placed here, was moved to Destiny's forward port. Destiny provided room for experiment racks, control panels, and avionic systems. It also brought a key upgrade, enough onboard computing power to finally activate the control moment gyroscopes. After almost a year, the 95-kilogram gyroscopes were finally spun up to 6,000 revolutions per minute to control the attitude of the station. Each gyroscope gimbals independently, and together their combined angular momentum generates torque that allows the station to rotate. While only 3 gyros are needed, a 4th one is used as a backup. Now, with full control of the station, out of the infinite possible orientations the ISS can travel in, what is the best way to orient the station while orbiting? If the solar panels are tilted like this, facing the direction of travel, the drag increases and tends to pitch the station up. So, 4 gyros are moved together to pitch the ISS down. Some forces are obvious and we can relate to them here on the surface, like the drag on the solar panels, but other forces we don't experience much. Earth's gravity is not uniform, so as the ISS orbits, it can experience a gravitational torque. Modules and trusses stretch out in different directions, and their uneven mass and placement create a constant imbalance. These gyros are constantly adjusted to orient the station in what is called the torque equilibrium attitude. This is essential for tracking the sun, managing thermal loads, aiming the antennas, and lining up visiting spacecraft for docking. The system was a step forward, but not without issues. In June 2002, astronauts reported hearing a growling sound inside Unity. One gyroscope began to vibrate, and hours later, its bearings failed due to overheating. Failures like this is why upkeep of a permanent crewed space station is so hard. NASA had to plan an unexpected spacewalk to physically remove the gyros. Then, a couple of weeks later, the resupply mission had to remove food and supplies to carry 2 extra newly designed gyroscopes that again needed a spacewalk to be replaced. Using gyroscopes does have a limit and can't be used forever. Over time, the external forces build up angular momentum within the gyroscopes. This momentum accumulates until the gyroscopes reach their torque limits, a condition known as saturation. When all 4 gyros are aligned, they can no longer generate enough counteracting torque. To fix this, the station relies on carefully planned burns from thrusters located on the Zvezda service module. These thrusters serve a dual purpose. First, they apply a torque to the station, so that while the thrusters are firing, the gyroscopes can move back to their original positions in a process called desaturation. Second, the same firings are timed and directed to push the station into a slightly higher orbit, counteracting the gradual drop in altitude caused by atmospheric drag. For a couple of minutes, the thrusters increase the station's velocity by 1 to 2 meters per second, and for those few moments, the normally weightless astronauts get to have fun while the ISS accelerates forward.
It's a fraction of a G. It's very, very light acceleration, but it's really neat to be, say, in the middeck of the shuttle, and everything is quiescent, peaceful, and then we perform a slight adjustment of attitude, or a more abrupt maneuver would be the deorbit burn, where actually, very gently you get thrown against the walls of the middeck. So you're just kind of slowly pushed back against the wall. So it's a very foreign sort of sensation, especially after you've been in space for a couple of weeks and you're really used to the weightless environment, and then all of a sudden you have just a little bit of a perception of a G-force.
This is what the station looked like at the beginning of 2001. Up to now, the only way to move modules or pressure mating adapters around was using the Canadarm attached to the space shuttle, but that was about to change because STS-100 was about to give the ISS an extra helping hand. The Canadarm 2. This thing was a robotic evolution over its predecessor, and guess who's the astronaut next to Chris Hadfield installing this major new upgrade? Scott Parazynski.
But to get it up there was quite a task because it's a very large robotic system. It had to be folded onto itself. And we brought it up in a carrier, and it was basically folded in 4 parts. So it was not only the elbow, but then each of the arms were broken as well. So it was kind of bent upon itself. And so there's a lot of coordination between the spacewalkers and those flying the robotic arm inside the space shuttle, and then controllers in Houston and even in Canada as this whole system came to life. So initially this carrier was placed on top of the laboratory module of the ISS, and we had to connect a couple of connectors for power and data to allow it to receive energy, and so we could start to talk to it and warm it up. But then Chris Hadfield and I had to perform 2 spacewalks to essentially unfurl it and allow it to really come to life. So we had several of these, we call them super bolts, but they were massive long bolts that were pinning the quarters of the robotic arm down onto the carrier itself. So we were able to remove these, put them into what we called a quiver on the side of this carrier, and then we had to unfurl the arm, so basically bring it into its normal arm-like state.
When you say unfurl the Canadarm, do you mean it is powered and you're just like helping it there, or were you physically moving the arm itself without power?
We're mechanically moving it. In fact, I didn't mention it in my description, but yes, we were back driving the joints of the arm. So the arm, although heaters and things were powered, we were not driving the arm. We were actually physically moving it. And so one of the things that was one of the more demanding things I've ever done on a spacewalk was the lift of the booms of the robotic arm. So the 2 shoulder joints have a lot of resting torque, and I had to basically I called it the clean and jerk, but I had to physically bring it up, I think about 30 degrees, and that would allow me then to work from a foot restraint mostly and work on these expandable diameter fastener bolts, giving me access to basically do my job, while Chris would have access from the robotic arm above. So that was one of the critical first steps that actually ended up being a lot harder than we ever imagined in our training.
I'm actually really curious about this because I've never really thought about the types of specific training you'd need to do to prepare to be an astronaut. Of course you need to be fit and maintain your health and everything, but when they're designing the Canadarm, does it only, the motors only need a tiny bit of torque, right? Because of the weightlessness. But what sort of strength training do you need to do to lift things in space, I guess? What's the most important thing?
Well, yeah, weightlessness is a bit of a misleading term because you are experiencing mass and inertia. And so forces can be quite substantial to a spacewalker. So imagine you're moving a 500-pound element, 225 kilos or something like that. That has a lot of inertia. So if you get it going at a certain rate, you're going to have to be very, very careful and deliberate and to react through the center of mass of that object. Or you could actually be ripped out of your foot restraint. You could actually go tumbling off as well. So there are substantial forces that the robotic arm has to compensate for. Imagine, receiving, a new module that has to be installed on the outside of the space station. It's got to manage that entire mass, sometimes off of its center of mass as well. So it's quite a complex, high torque kind of activity. So yeah, the spacewalking looks graceful and peaceful, but actually at times it can be very high workload.
In terms of fitness and strength, was there anything that caught you off guard, like some particular muscle that you weren't used to exercising that got exercised a lot in orbit?
No, I think by and large, we've felt very well prepared for the task that we were about to go do. But one of the things that I always championed was pursuit of kind of upper body and including forearm and hand strength. And it's one of the reasons that I recommended and we were able to bring into our astronaut gym a rock climbing wall. So the same types of muscles that are used in rock climbing are those that fatigue the quickest in a really intense spacewalk. So the hand intrinsic muscles and the forearm muscles, you really want to make sure that you're prepared there.
Scott and Chris latched the arm to the ISS here on the Destiny module. If you look closely, sticks and cam knobs are dotted everywhere on the ISS. This is where the Canadarm can attach to. Both Canadarms use a system to grab onto satellites that relies on two rings, with cables connecting them. As one ring rotates, it moves the cables and creates a self-centering snagging mechanism. But Canadarm 2 was not meant to live in one place. Unlike the original Canadarm, which was fixed at one end, Canadarm 2 had identical latching and end effectors on both ends, meaning it can move from one grapple fixture to another, increasing the range and flexibility of the ISS for future expansions. The new arm was a major upgrade from its predecessor. With 7 motorized joints, it could bend, rotate, and extend with a carrying capacity of up to 116,000 kilograms. These upgrades made it indispensable for installing truss segments, relocating equipment, capturing visiting spacecraft, and supporting spacewalks with unmatched versatility. But because the arm could move around the station, that meant that each grapple fixture also had to include a way to power the arm. For this, a new design for the grapple fixtures was introduced. 4 electrical connections were placed on the side of the sticks. Once the grapple motion happens, alignment guides ensure the arm connects centrally and securely. Once latched, the arm can draw power, exchange data, and receive commands. Throughout all of these construction projects and spacewalks, the only way in and out of the station was through the space shuttle. That changed soon after one of Scott's missions.
So the flight right after ours was the installation of the joint airlock. And so that became really the kind of the nidus for all of the spacewalks to follow. So the spacewalks that Chris and I did during STS-100 were outside of the shuttle's airlock, which is very capable and it worked just fine. But the problem with that is we had to seal ourselves off from the International Space Station during that period of time. And that basically prevented the rest of my crew members from transferring gear, from doing experiments, working together with our counterparts aboard the ISS. So the combination of our mission was called 6A, the 6th assembly flight, and 7A, the one to follow that installed the joint airlock. That then made it possible for us to do assembly spacewalks outside of the space station airlock while the rest of our crewmates could be, traveling freely between the two spacecraft, getting lots more stuff done.
This is what the station looked like when STS-104 was approaching it in 2001. The shuttle arrived here, and in its payload bay, it carried the airlock Scott just mentioned. The Canadarm 2 slowly rotated the Quest airlock into place and installed it here to the starboard port of Unity. The Quest airlock is split into two parts. Here is the larger equipment lock, where astronauts suit up before heading out. Then, they pass through a hatch into the smaller crew lock, seal the door behind them, and slowly vent the air to vacuum. When the outer hatch finally opens, the first thing they see is Earth, filling the view below, silent and impossibly bright. But the growing crew and equipment also required a sturdy structural backbone, and a frame that could carry power, data, and mechanical loads across the station. In April 2002, STS-110 delivered the S0 truss, the central segment that would become the integrated truss structure. To fully utilize this growing spine, the robotic systems also needed to evolve. In June 2002, STS-111 brought up the mobile-based system. This addition allowed Canadarm 2 to move along rails spanning the truss structure, no longer confined to a single mounting point. With this newfound mobility, the arm could reach wider areas of the station. Then came the need for cooling and lateral expansion. Two new truss sections brought with them one of the station's most important lifelines, a complete external ammonia cooling loop. Ammonia was chosen for the station's external cooling loops because it stays liquid in the extreme cold of space and is much lighter than water for the same heat carrying capacity. In each truss, a pump pushes the ammonia through a closed circuit, but its toxicity means it must remain entirely outside the pressurized modules. If a leak ever occurs inside, it's safer and easier to clean water than ammonia. So, the system is designed with an inside water system that carries its heat and exchanges it with the ammonia outside the pressurized sections. As ammonia heats and expands or cools and contracts, nitrogen tanks connected to the storage tanks absorb the volume change by compressing or expanding behind flexible barriers. This keeps the pressure in the loop stable in all operating conditions. For the radiators to work, they have to face the cold of space. Point them at the sun and the whole cooling system becomes useless. That's why the radiator wings need to rotate, constantly adjusting to keep their broad surfaces aimed into the void no matter how the station moves. But that creates a new challenge. How do you keep liquid ammonia flowing through plumbing that also has to spin? The answer is the thermal radiator rotary joint. Inside, flexible hose couplers let ammonia flow through rotating lines. Power and data cables pass along the joint through a transfer assembly, while motors and gears control the swing itself. Altogether, the joint allows each radiator wing to sweep back and forth 210 degrees. Between 1998, when Unity joined Zarya, and 2003, 14 shuttle missions assembled 4 main pressurized modules, along with vital truss and airlock components. Some of these pieces were launched separately and connected for the first time in orbit by nations that were fighting a Cold War less than a decade before. Construction wasn't flawless. Destiny's cables were miswired, Quest developed small leaks, and Canadarm 2 lost a motor soon after activation. But those setbacks were minor compared to what came next. A small piece of foam would halt assembly and reshape spaceflight. This is the story of the ISS that we will cover in the next episode of Real Engineering that you can watch early on Nebula, and there's never been a better time to sign up. You can now get 50% off the annual subscription for just $30 for the entire year, a perfect gift in the lead up to Christmas. And there is plenty new to watch. Patrick Willems' latest short film, The Dinner Plan, featuring Griffin Newman and Zach Cherry. Scav, the new series from the Jetlag team, following the world's largest scavenger hunt. We also just wrapped filming for Season 2 of Abolish Everything, a comedy debate show that I agreed to appear on with zero comedy experience, so if you want to laugh at me for the right or wrong reasons, that's something you can look forward to. And of course, Nebula is still home to some of the best curated, informative documentaries on the internet. Bobby Broccoli's 17 Pages, Real Life Lore's Mad Kings, Wendover's Logistics of X, and my own Logistics of D-Day and Battle of Britain, with plenty more originals from myself and other creators planned for 2026. If you're unsure about Nebula, we are now offering a 3-day free trial, and we dare you to try to watch all of that exclusive content in those 3 days. I view Nebula as a sanctuary away from the noise of algorithmically driven social media sites, both for creators and the audience. No AI bots and AI generated spam clogging your feeds. We only work with the best creators that take pride in their work because they love their work. So if you want to support creators who still value craft and get access to some of the best video essays and documentaries on the internet, head to nebula.tv/real engineering, or click the link in the description or scan the QR code on screen to sign up. You'll get 50% off an annual subscription. That's $30 for the whole year. You can even sign up to a lifetime membership if you don't want to deal with yet another streaming platform subscription.